Hello everyone, my name is Alexandre Levada and I'm here to present the paper Entropic Laplacian Eigenmaps for unsupervised metric learning. So, an introduction, Laplacian Eigenmaps is a manifold learning algorithm for nonlinear dimensionality reduction, and it is based on the Laplacian matrix of graphs. So if you approximate, the idea is that if you approximate the manifold, the underlying manifold in a data set by a KNN graph, then it's possible to find a mapping of the vertices of this graph to the Euclidean space that preserves locality. So nearby points in the graph will remain close together after the mapping is performed. Such map, as we said before, is given by the eigenvectors of the graph Laplacian. So, Laplacian eigenmaps is not perfect. It has some limitations. One of the most prominent limitations is that it can be quite sensitive to variations, noise and outliers in the observed data. So the question here is how to improve Laplacian eigenmaps for unsupervised metric learning, which means prior to classification problems. So the definition of the Laplacian matrix is the difference between the degree matrix and the adjacency matrix. Laplacian matrices have been studied in spectral graph theory, and the spectra of this matrix is known to be several interesting mathematical properties. Some of them, the most important property for us is this first here, which means that this quadratic form here, if we consider f a vector in Rn, this quadratic form here is nothing more than a measure of, let's say, how scattered the points are. So if we think in terms of preserving locality, it means that points that are close together in the input space must be close together in the output space, where Fi and Fj are the coordinates of these points in the real line. That's the criterion. We want to minimize them. So the goal is to minimize this objective function here, where Wij is the weight between two vertices of the graph, and Yi and Yj are the coordinates of the output space. We want to find this matrix Y of coordinates, low dimensional representation for our input data. So by solving this problem, we find out a constrained optimization problem. So we want to minimize this form subject to this constraint. And it leads to an eigenvector problem. So the solution is given by the smallest non-zero eigenvalues of the Laplacian. Entropic Laplacian eigenmaps, our proposed method, basically what we want to do is to replace the Euclidean distance in the graph by, let's say, the relative entropy or the KL divergence between patches of this graph. So to do so, we denote a patch. What is a patch? It's the matrix composed of the central element and its k nearest neighbors. So we can arrange this matrix Pi like this. The idea is to assume that each column of this matrix is a sample of a multivariate Gaussian. So we can estimate the mean and the covariance matrix of each patch. And given that we have these parameters, we can find a closed form expression for the symmetrized cubic line divergence that we will use to weight the edges of our KNN graph. So a summary of the algorithm is given here. We first build a KNN graph, then we choose the weights. We weight the edges of this graph using this expression here. It's a Gaussian kernel defined in terms of the symmetrized KL divergence. Compute the matrix D, the degree matrix, compute the Laplacian matrix, and then we select the D eigenvectors associated to the non-zero eigenvalues of this Laplacian. That's why we call this algorithm entropic, because of this measure here, this similarity measure. So we performed some experiments and to verify the behavior of the proposed method, again, in comparison to other manifold learning algorithms in the literature. So two sets of experiments. In the first one, we want to see the quality of the clusters obtained after the dimensionality reduction. So we use the silhouette coefficient metric. And the second experiment, we want to check the average classification accuracy for 4 different supervised classifiers: KNN, decision trees, Bayesian classifier, and random forest after dimensionality reduction. So we compared our proposed method against PCA, kernel PCA, isomap, LLE, Hessian eigenmaps, and regular Laplacian eigenmaps. The first table here shows the results, so shows the silhouette coefficients obtained for several different data sets. These data sets are freely available at openml.org. More information regarding the number of samples, the number of features, the number of classes can be found at openml.org. So as we can see, the proposed method can produce higher silhouette coefficients, which means clusters, better clusters. Similarly, for the classification accuracy, we can see that for these data sets, the proposed method achieved better classification accuracy, indicating that the features are somehow more discriminant. To test if the differences were significant, we performed statistical tests, and in both cases, first, with silhouette coefficients, the test indicates that the proposed method produced significantly higher coefficients than the other ones, for a significant level of 0.01. In terms of classification, the same behavior was observed. The entropic Laplacian eigenmaps produced significantly higher accuracies. Here is a qualitative result that was obtained in a small sample size data set. And in the left here, we have the result of regular Laplacian eigenmaps. We can see that the clusters are very mixed together here. We can't distinguish very well cluster class 1 and class 2. Here at the right, we can see the result with entropic Laplacian eigenmaps, where the separation is clear. We see that the quality of the clusters is improved and data is easily discriminated here in this parametric, in this feature space. The idea is to perform metric learning, which means we want to learn an ideal metric before classification tasks. So clearly, the metric that was learned here by the proposed method is much more meaningful in terms of discrimination than the metric learned here in the regular Laplacian eigenmaps. So our conclusions, the results were promising, but we have one limitation with our method. That is the definition of the optimal value of k, the patch size. So we don't have an automatic method for estimating the optimal value of k, the patch size. What we are doing currently is perform a line search in the interval 2 to 30. We test several values and choose the best one. Future works may include the use of other information theoretic distance to perform metric learning, such as Bhattacharya-Hellinger and Cauchy-Schwarz divergence. And of course, to study a method for estimating the value of k automatically. Well, that's it. I would like to thank for the attention and feel free to ask some questions if necessary. Thanks once again.